All right, good evening, everyone. My name is Eric. We are on day 3 of our memory layering week. On day 2, you guys learned about short term session memories. For day 3, we are going to be talking about long term memory and persistent knowledge storage. We have our learning objectives. We have 2 lessons for the day, 1 lab and 1 assignment. For our learning objectives, we define long term memory and AI applications, choose the right storage medium, design schemas for user, and retrieve and inject relevant long-term data into prompts. We also have additional resources for RDS and PostgreSQL. We have our assignments. So long-term memory lets the AI recall facts and context beyond a single conversation. It's stored outside the model and retrieved on demand, often keyed to a user ID or entity. We'll explore what to store, how to store it, and how to retrieve it for personalization, continuity, and business logic, all while managing costs and avoiding data bloat. So let's go ahead into our first lesson. Lesson 1 covers long-term memory, persistent knowledge storage. Long-term memory allows an LLM application to retain knowledge across sessions, devices, and time, even after a user closes the app or logs out. This type of memory is essential for building personalized assistants, adaptive learning systems, and enterprise AI tools that improve over repeated interactions. Unlike short-lived session memory, long-term memory is stored in durable databases or vector stores and retrieved via embeddings or key value lookups. It can be selectively updated, deleted, or expanded, allowing controlled persistence of user knowledge. Right below, we have our diagram of key features of long-term memory. We have storage, persistency, retrieval, and personalization. For storage layer options, we have SQL, NoSQL, and vector database. We have persistence. So instead of just only being able to access memory that is stored within your session, so in minutes, you're able to actually go back maybe even years uh, if there is a data that has been stored long term. So for an example, if we have a recipe assistant chatbot, so you're interacting with the chatbot and looking up good recipes on how to make a certain dish. You will, you can, in the first session, you probably specified how many people are in your household, so maybe 4. If you keep on chatting with this chatbot and have used it over months, it will remember that your household equals 4, so that it knows to give you the correct recipe that feeds 4 people. And it won't have to ask you every single session how many people are in your household. So that's what persistence is about. We have retrieval mechanisms, so semantic search and metadata filtering. Think about semantic search. Whenever you see the word semantic, just think about similarity. Example use cases, personalization, historical recall, and knowledge-based integration. So our key concepts. Long-term memory is a persistent storage of facts, preferences, and past interactions that an AI can retrieve later to maintain context over weeks, months, or years. Again, to think about how you specify in your first session that you have 4 people in your household. Why it matters: enables deep personalization without requiring users to repeat themselves, supports knowledge accumulation for domain expertise, allows historical pattern recognition across multiple interactions, and facilitates compliance-friendly archiving of relevant interactions. So for our implementation patterns, we have about 5 components. So we have database choice, indexing, embeddings, versioning, and CRUD controls. So for database choice, SQL or NoSQL for structured storage, vector database for semantic embeddings. Indexing, organizing memory for efficient retrieval, so by user, ID, topic, or timestamp. embeddings, converting text to vector space for semantic similarity search, and versioning, keeping historical states of knowledge for rollback or editing, auditing. Our last one is CRUD controls, letting users create, read, update, delete their persistent memories. An example tech stack for databases would be PostgreSQL, MongoDB, DynamoDB. Vector stores, you can use Pinecone, Weaviate, FAISS, Milvus. Orchestration, you can use LangChain, LlamaIndex, custom retrieval pipelines. And security, data encryption at rest or in transit, and role-based access. So for best practices, we have scope, define what qualifies as worth remembering to avoid bloating storage. Metadata tagging, store related metadata for better search. User control, let users manage their stored knowledge. Privacy compliance, respect GDPR or CCPA and retention policies. Performance optimization, use indexing and caching to avoid slow retrieval. We'll go to our next lesson. For lesson 2, we have indexing and retrieving long-term knowledge. Long-term memory in LLM applications is only valuable if it can be efficiently searched and retrieved when needed. Without an indexing strategy, stored knowledge becomes a large, unorganized archive that is difficult to access in real time. This lesson covers how to index long-term memory for faster lookups and how to design retrieval logic so only the most relevant information is injected into prompts. Our core idea, the two key things you need to get out of this lesson is indexing and retrieval. So indexing, structuring stored information so it can be retrieved quickly based on search criteria, and retrieval, selecting and returning the smallest, most relevant subset of stored data to avoid overwhelming the LLM context window. So think about indexing as just setting it up so that you are able to find it quicker later on and query it quicker. Retrieval is actually the process of getting that data. We have example scenarios. So for our customer support bot scenario, we have long-term memory contains thousands of past customer interactions. Without indexing, searching for a refund policy requires scanning every stored conversation. With indexing, though, the system uses keyword tags or embeddings to find relevant results in milliseconds. Our knowledge-based search scenario, a documentation assistant stores entire product manuals. Indexing allows retrieving only the section relevant to that user's current question. Our methods of indexing. First up, we have keyword indexing. It creates a separate table of keywords linked to entries, works well for structured and predictable search terms. So for example, if a user asks about billing problem, it will look up anything that contains billing and it is found in known issues. So it returns users with billing related issues. For metadata tagging, it assigns attributes like topic, date, source, and enables filtered searches. So an example, all entries about security from the last 30 days. If you filter the topic to support and the date to being greater than 2024 January 1st, it will return recent support related entries. We also have embedding based indexing, so converting text into high dimensional vectors using an embedding model. It allows semantic search, which finds relevant info even without exact keyword match. So an example, a user asks, I can't pay for my subscription. Vector search finds a semantically similar billing, payment, subscription issues terms, so it returns the top 5 most relevant past interactions. We have retrieval best practices, so it rank results, so order by relevance score before injecting into prompt, limit scope, pass only top end results into the LLM to avoid token waste, and context filtering, use metadata to narrow down candidates before scoring. What are the trade-offs between each method of indexing? So for keyword, Our pros are that it's simple and fast, but a con of it is that it requires exact matches. For metadata tagging, a pro is that it's flexible, human readable, has flexible human readable filters, but a con is that it needs consistent tagging discipline. Embedding based pros handles natural language queries. Cons requires model calls and vector storage. So why is indexing important for long-term memory? It enables efficient searching and retrieval. Which indexing method is best for exact keyword matches? Keyword indexing. What is the main advantage of embedding-based indexing? It handles natural language queries. So a summary, effective indexing is crucial for making long-term memory valuable in LLM applications. By implementing the right indexing strategy, whether keyword-based, metadata-driven, or embedding-powered, you can ensure that stored knowledge is quickly accessible and relevant when needed. The key is choosing the indexing method that best fits your use case and data structure. Let's go ahead and move on to the lab. For our lab, we have a fuzzy search knowledge store system, and our goal is to build a knowledge search system using fuzzy string matching for intelligent content discovery. So we have our prerequisites. To get started, we're just going to go into our directory within our curriculum that has the lab. So in week 12, day 3. So let's go ahead and I'll show you what I did to do that. So I went into the directory of where the lab was stored, and I typed in pwd for present working directory. I got the path of where I am at. I copy that, and then I go into the terminal. And I type in CP for copy. I throw in a -R flag for recursive because it is a directory, and if you don't include that, it's not going to be able to copy it. With the flag, it is able to copy everything that is stored within that directory. So make sure you include it. We're going to paste our path from our curriculum that contains the lab. Press space, and then we're going to set the destination. So we want it in this directory, and you just press a dot. So it should copy everything to this specific directory that we are currently in. I already did that, so I'm not going to do it again. Let's just make sure it's there, ls, and we do have our lab. So let's go ahead and cd into that lab, and I'm going to go ahead and open it in VS Code. Let me rearrange my screens real quick. Okay, so once we are in our lab, we want to go ahead and make our virtual environment. Go ahead and run the command to do that. I know on the GitHub page for the lab, it says that we are using Python 3, but I tried doing that, and it was giving me some compatibility issues. So I found out that Python 3.11 is going to work. That's why I have it right here. If you're using Docker, it should work, however. So I add this dot before this venv just so that it hides that directory, and it's just common best practices when setting up your virtual environment. Code editors are usually by default looking for a .venv versus a venv. So I'm just going to include that period at the beginning. So once you have that command, go ahead and create it. You should see a venv directory pop up on the left side. Go ahead and activate it using source.venv bin activate. And you should see it change from default to your virtual environment. If you look at your if you look at the lab on GitHub, you'll see that has a fish option and a bash option. I use the bash. What fish is, it stands for friendly interactive shell. So it just makes the shell easier to use by default, and it will provide suggestions as you type. So for example, if you're typing mkd, it'll give you suggestions for maybe mkdr for make directory. It just makes it easier to use the shell. So let's go back to our lab, and after we have activated our virtual environment, let's go ahead and install our dependencies using pip install -r requirements.txt. Let's go ahead and run that. There's an upgrade for a pip, so I'm just going to copy and rerun that command. Make sure everything is updated and successful. So we are good to go. Next step is to just test out our lab runner.py. We'll do that using Python lab runner.py to run it. Let's see what we get back. So notice that we had a JSON file that got created, and we got something back returned in our terminal. So let's actually go through what happened. Let's go through the lab runner file. But actually, before we do that, let's go ahead and see what was inside our requirements.txt. Can run that by cat requirements.txt. We have Fuzzy Wuzzy and Python Levenstein. So Fuzzy Wuzzy is just a Python library for string matching, basically comparing strings that aren't exactly the same and scoring how similar they are. Python Levenstein calculates how many insertions, deletions, or substitutions are needed to transform one string into the other. Think of Fuzzy Wuzzy as the high-level API and Python Levenstein as the performance engine. So now that we saw what we actually installed through our dependencies, let's go ahead and rerun that labrunner.py. I am deleting this so that whatever got created within that specific file is not just gonna duplicate within our knowledge store, which we will get in a second. So let's go to our labrunner.py. Let's go run that command. It's successful. Scroll all the way up. So first thing we notice in our file is the docstring. So docstrings are very useful and common practice just to let everybody know what is happening either within the file or within the method or function. So this overall file is a script that demonstrates all the features of the fuzzy knowledge store class, which can be seen in this other file, and we are actually going to go over this as well right after we go over the labrunner.py file. So we have our imports. And we start out with this function called print separator. This just creates the titles. So as you can see, it prints a formatted separator with title. It prints out 60 equal signs on the top, prints out the title, and then prints out another 60 equal signs right below it. We have our print knowledge entry, so it prints a knowledge entry in a formatted way. So if we look at what's listed here, we have ID, topic, category, content, and the keywords. If we look at our terminal, we have ID, topic, category, content, and keywords as well. This part right here just shows the search score as well as the match details down below. And these only show up if this show details down here is set to true. So we actually have our main function. It's the main lab execution function. It's what executes everything after we run the file. So let's go all the way back on top of our terminal. So first off, it prints out a line that says starting fuzzy knowledge store lab. It then initializes the knowledge store. So it creates a variable called store, calls in that class from our other file, fuzzy knowledge store. And it just points to where our knowledge is going to be held. So think of it as our database. So it's going to get stored in a file called fuzzyknowledge.json. This fuzzy threshold is set to 60. A threshold of 60 just means that it only returns results that are at least 60% similar to our query. So lines 34 just initializes that knowledge store over here. After that, we're just calling that print separator function again, passing in the title, which we get this as the output. We create a sample data variable that just contains all of our sample data or sample knowledge entries. So all of this got added to our store, as can seen from this loop. So we have our content, keywords, topic, category, date added, search score, and this all comes from over here. So it's saying for the data that's within the sample data variable, everything that's stored in that list, I want you to add it to this store. So this add knowledge method comes from our other file, fuzzy knowledge store, that contains all our methods that is called within our lab runner. So it just adds all those entries above. Next, we print out another separator for step number 2, testing fuzzy search. We create a test queries variable. This is what we're going to be querying. So first, the first one is we have a typo in Python. It's missing the O. We have an abbreviation for machine learning. We have an exact match for Docker, a partial match. This probably is a partial match for web development. We have another partial match for artificial intelligence. We have a keyword search, data, and then a typo in framework. So for each query in this test queries, we're going to print out a line that says searching for whatever we are querying. The results get stored in a variable. So within this results variable, store calls a search fuzzy method that is again listed within our fuzzy knowledge store .py. So right here, we pass in our query. So in this case, we passed in Python without the O. We have a limit of 3, so that's saying don't give me anything more than 3. Don't give me 4 results. If 4 results match, make sure it caps out at 3. So if results is true, if we do get results, it'll give us the length of the gives us however many results are getting returned, and it prints them out. So for example, for Python without the O, we got 2 results, gave us back ID 1 and 4, a topic on Python programming, and Flask framework. If there's nothing, it'll print out no results found. After that, we have another print separator. For our third step, we change our query to just machine learning, and it prints out a line testing different strategies for machine learning. And we actually have our strategies. We create a strategies variable, and it says best, partial, and token sort. So let's go back up to our step 2 when we were querying Python without the O. Notice how we got back the ID, topic, category, content, keywords, and then we have a search score and match details. Remember that I mentioned the show details equals true. So if this was false, these 2 would not get printed out. But since it is true, it'll show us our search score and match details. For match details, think of it as different strategies for the search. So notice in our strategies variable, we have best, and then we have partial, which can be found within our match details. So partial right here. And then we also have token sort, which is right here. Best is just getting the highest score from those match details. But key point is think about everything in the match details as a strategy. Let's actually go over what these details mean. So exact is the score if the query matched the text exactly. It's low because Python without the O isn't exact and doesn't equal Python with the O. So that's why it got a score of 6 out of 100. Partial got 80 out of 100, so it's a score for partial matches. Python without the O sort of matches a part of Python with the O, so that's why it's a higher score. Token sort is we got a 6 out of 100. It's a score when tokens are sorted and compared. It's not too significant here. We have our keywords, so it's a score based on matching keywords in the entry. It's high because Python is a keyword. So let's actually check our, so we have Python as a keyword in our ID 1. So that's why we got a higher score. We also have topic. We got a 43 out of 100. A topic score is based on matching the topic field. So some of this query right here matches with Python programming. Let's take a look at our knowledge base again. We have Python programming, so it kind of matches it. So that's why we got a score of 43 out of 100. We also have category. So category is a score based on matching the category field, kind of like topic. And we got a 15 out of 100 because it kind of matches Python without the O. So we're category programming languages. We got the a very low score because it doesn't even have Python in it or anything compared to the topic. So we also have our search score. The search score is calculated from all these individual components down here in the match details. If we go back down to step 3, we have testing different search strategies. So again, within our strategies variable, we have best, partial, and token sort. Best, think of it as just getting the best scores out of those match details. So for each strategy in that strategies variable, we store it in a results variable. So it's going to search our knowledge store. We're going to send in our query, our strategy, and we only want a limit of 2. So only 2 results max. And then we print out our strategy that we are using, all in uppercase, and we print out our results. So we print out the topic of machine learning, and then we also print out our score. So our search score. So we got 100 for machine learning through the machine learning query. That's in all lowercase. Let's actually try to find machine learning in our knowledge store so we can just get a better visualization. So it matches exactly what is stored in the topic minus the capitalized M and L. So that's why you got a score of 100 for best and partial. But notice how token sort doesn't have anything returned. It is because we have set our threshold, remember, to 60%. So we don't want anything that has a similarity rate of less than 60% to be returned. That's why it did not return anything. So let's actually try to change our fuzzy threshold. So the reason why token sort didn't return anything is that the text it's looking at is long. So for example, for the machine learning, it's looking at all this different text, it's looking at all this text over here, and that kind of dilutes the score to be smaller. Think of it like trying to find words in a haystack. We would either need to make the haystack smaller, so use less words over here to increase the score, or we can just lower the threshold, which we will do right now. But first off, let's go ahead and delete this so it just doesn't overwrite or add on to it. So let's actually change this to something like 20. Let's see what we get. Let's run the lab runner again. And we should get something back for our token sort. So we actually did get something back. Now we have the reason why we didn't get it back earlier was because the score of 20 is less than 60. But now that we changed our threshold, we are able to see it. Notice how for the other strategies as well, it's showing Python programming now because it got a score of 50. So that's how that threshold works based on similarity. Let's change this back to 60. And let's go ahead and delete our knowledge base again. Let's go ahead and clear this up real quick. And rerun our lab runner. Let's go back to check 3. Since we set that threshold back up to 60, it's not giving us anything less than that. So when dealing with a large file like this, your best friend is Command F just to look for whatever you need and quickly navigate to it. So for example, let's do 4 period dot, because we know we are on step 4. So it uses the print separator function to create that title. We're printing out the categories available. So using this list all categories method from our class, we're able to print out all our categories, which can be seen right here. We also have list all topics. So using that method, we're printing out all the topics. Our next line prints out a statement that says searching by category, and then we specify what category. We're using programming languages. And we have a method called search by category that gets called for the store. And we pass in our category programming languages and we store it in our results. So for all the results, for each result in that variable, we print it out. So we got something back. We got ID1. So if we look at the category, it does match programming languages like we queried. So now we're moving on to check 5. We're using the print separator, creating the title. This one, we're updating the entry in our knowledge store by using this method. We're specifying our ID and what we want to change. So we want to change the content to Python is a amazing programming language. Let's actually take a look down here because it gets printed out. So we see that the content says Python is an amazing programming language, but if we scroll up towards the beginning of our output, it should say something different because we just updated it later on down the file. So yep, this does not match what we just changed it to. This one says Python is a high level. And we changed our content to Python is an amazing programming language. Let's go back to step 5. So we verified that our content got changed, but if we also go to our knowledge store and go to and look through ID1, we notice that Everything else does not have a date modified line, but ID1 does because we updated that content. So let's go ahead and go to check 6, final statistics. This just prints out a summary of everything. So we have a total of 5 entries within our knowledge store. We have 5 topics, 5 categories. We also show where our knowledge store is held. So it's held within our fuzzy knowledge.json. And we also show our threshold at 60. For check 7, we're just testing with lower thresholds. So we print out a line that says testing with low threshold and passing in this right here, this variable. So we're setting it to 30 for this one. And then we print out our results. So we were able to get that machine learning since it's less than 50. And we reset our threshold back to 60. Now all these are just mentioned that the lab has been completed. So we went over what is happening within this file, kind of as a precursor so that you can understand better what's happening within the methods of this class and kind of have an overall view of what's happening. So we tested that lab runner works. Let's go ahead and continue on. So what you'll learn today is fuzzy string matching, understanding how approximate text matching works, JSON file storage, managing persistent data without databases, search algorithms, implementing intelligent content discovery, error handling, building robust applications that handle edge cases, and testing, verifying your implementation works correctly. So understanding fuzzy search also called approximate string matching, finds strings that are similar to a given query. If they don't match exactly, this is incredibly useful for typo tolerance. So finding Python without the O when searching for Python. Partial matches, finding machine learning when searching for ML. And similar concepts, finding artificial intelligence when searching for AI. So how does it work? The Fuzzy Wuzzy library uses the Levenshtein distance algorithm, which measures how many single character edits, so insertions, deletions, substitutions are needed to transform one string into the other. And below we have an example. We just import our library. And our first example is an exact match. So Python equals Python, so we get a score of 100. If we have similar strings, so we have a Python with the O and one without, we have a score of 83. This one right here is just missing the H instead of the O, and we still have a score of 83. For partial matches, Pi is in Python, so we get a score of 100. And then there's no ML in machine learning, so it gives a score of 0. There's no ML listed consecutively, so that's why we have a score of 0. Token sort, it handles word order, so machine learning is the same as learning machine. Using this token sort strategy, so this is 100. So our next step is to create our fuzzy knowledge store.py. This contains our class, the fuzzy knowledge store. Let's actually just go ahead and look at that within our VS Code. So we have our imports, and this right here is underlined yellow because it's just VS Code saying that, hey, I might not be able to find this module, and it's not 100% sure about it, but it still works since our labrunner.py was able to handle everything when we ran that file. So we create our class fuzzy knowledge store. We have our docstring. It's a knowledge storage system that uses fuzzy string matching for intelligent search. We have our features, so fuzzy search with configurable threshold, multiple search strategies, so exact, partial, token based. We have our JSON file persistence, and then automatic indexing and relevance scoring. We have to initialize the knowledge store with init. And this right here is just going to point to our JSON storage file. And then fuzzy threshold is just the minimum similarity score from 0 to 100. In our case, we set it to 60 earlier for fuzzy matches. And then we also have a self.load knowledge. It just loads existing knowledge from that JSON file. So after that load knowledge method, we have our save knowledge. It just saves and writes the current knowledge to the JSON file. Think of it like saving your progress in a game. It just stores whatever is already in memory to disk. It pretty much sets up that JSON file. So if there's something in that in that JSON file, it'll save it. If not, then it's just going to be blank. We also have our add knowledge method up next. We pass in our content, our keywords, topic, category. It just adds new knowledge to the store. That's the point of this method right here. It'll return the created knowledge entry. So for our entry variable, we have our ID. Again, just kind of reference what in our terminal. We have our ID, we have our content, we have our keywords, we have our topic, and then date added, and our search score that will be start off at 0 but will be calculated during search. And we will append that that entry into our knowledge store, and we call that save knowledge to ensure that any modifications get saved. For our search fuzzy method, we have docstring. It just says search knowledge for fuzzy string matching. So this is what actually queries everything, and it's the brains behind it all. Let's take a look at if not query.strip. So this line right here just makes sure that you're not giving an empty query. This .strip part just removes spaces in the beginning and the end. So we have a query line up next, and it's set to the variable query.strip, and it just makes everything lowercase. We initialize our results variable where our results will get stored, and it's just an empty list for now. So for entry and self.knowledge, it looks at each entry. It uses some methods for this from fuzz to calculate all the different scores for exact, partial, token sort, keywords, topic, and category. Again, you can find that in those match details. The next block of code just uses the test score, uses the best score based on the strategy. So again, best is for just getting the best score out of those match details. So for this one, it would be partial. If the strategy is partial, it just gets that partial score. If it's for token sort, it will get that token sort score. And if it's something else, then if it's a different strategy, it'll just get the best one still. So max score. This next block of code just ensures that we meet the threshold of our 60%, and it appends it to our results if it does match it. So we have our next line, we have a lambda, and this lambda is just sorting it's just sorting the score. So the highest goes first, and then the next highest, and so on and so forth. We return all of our results, make sure that we are within our limits, which we specified to as earlier at 1 point to 3 or 2, depending. So next method, we search by a particular topic. So we search for knowledge by topic with optional fuzzy matching. So the optional fuzzy search just lets it match the query, even if typed differently. So for example, that Python without the O, that's just what that optional fuzzy matching does. Same thing for search by category. And then next we have get knowledge by ID. So this will just retrieve a specific knowledge by that ID. So if we look for 1, it'll give us that topic on Python programming. And then for our next method, update knowledge, it just updates the existing knowledge entry. So depending on what ID we give, this is the method that was called whenever we updated that content for ID 1. Python is an amazing programming language. So that just updates and modifies each entry. The method delete knowledge just deletes that entry. List all topics gets all, it just returns a list of all of that specific topic. Same thing with categories, or it lists, this method lists all topics, just returns each and every single different topic is a better explanation. So it will just go through each entry and print out whatever's in the topic, and then for the list all categories, it will print out whatever is in that category. Get stats is just it's a method that just shows all the summary. So remember that total entries, topics, categories, where our knowledge store is saved, and our threshold. So we went over everything within our fuzzy knowledge store, that py, and what's happening in the background. Think about LabRunner as the demo or interactive sample. And then we're going to actually get into our test file. And this is just the automated test to make sure that the code works correctly. Now the relation between LabRunner and fuzzy knowledge store is that LabRunner is actually what's like the upfront code, and then the fuzzy knowledge store.py is all those different methods that can be called. So we already created our labrunner.py and actually went over it to see what was happening. We created our requirements.txt file, so we have our fuzzy wuzzy dependency and Python Levenshtein dependency as well. Now we're going to get into our test suite. So let's go over what we have inside it. It's just the test suite for the fuzzy knowledge store, and you can run it by this command. So first thing we have is our imports, and then we have our fixture. And just remember that fixture is just a reusable setup function that prepares some state or data your tests need before they run. Kind of think about this that is in a way that it's creating a virtual environment, or like not a virtual environment, but within each test suite, it's creating an environment so that we can make sure it works. So our first one, it just ensures that we can create a temporary knowledge store for testing. So our temporary knowledge store is called temp file. And we're setting a threshold of 70 within our class and storing it as a variable called store. Let's actually run this test just to ensure that everything is passing. So first thing we want to do is install PyTest. Go ahead and clear this up. Pip install PyTest. And then let's actually run our test file. Everything passed, so we're good to go. So after our temp store test suite, we have our test add knowledge. It's just testing that we can add entries to our knowledge store. So we create a variable called entry. We're calling that add knowledge method from our fuzzy knowledge store.py. We have we fill in our content, keywords, topic, category with just some test text. And this assert portion right here just ensures that the entry ID is 1. The whatever stored within content is test content, like up here. For topic, we want test topic. And then we only added 1 entry. So there should only be a length of 1 knowledge within our store. So just this assert just says, hey, make sure that these are the outputs that I am getting back. If it's not, then it'll fail that test. And it's pretty much the same pattern across all these different methods. So for test search fuzzy, we're adding knowledge, content, keywords, topic, and category. So for topic, we're adding a Python topic. And it gets stored in our results, and we're searching for a query Python. Again, we should only have 1 result or entry within our knowledge store now after we after we added it over here. And we're just ensuring that the test score is equal to or above 90%, which it should be since Python matches Python exactly. Look at all these different Python words. So next, instead of testing the exact match, we're testing the typo. We should only still have 1 entry, but this time our search score should be equal to or greater than 70. Next, we're searching by topic. We're testing our ability to do that. We add that knowledge. We have results, so we store our results in that variable, and we're just making sure that we only have one entry within our knowledge store. Next, test suite is testing our ability to update the knowledge. So testing update knowledge entries. So we're adding a entry with an original content, original topic, and everything original. Next, we're calling the update knowledge method, selecting that ID, and then changing the content to updated content. So now we're making sure this is successful, and then we create an updated variable, and we're making sure that the content of the updated variable matches what we changed it to, which is updated content. Next method just tests the ability to delete the knowledge. So we're adding that entry, and then by the end of it, we're just ensuring that no entry is available within our knowledge store since we deleted it using this method. Next method, test empty content validation. So we're just testing that whenever content is empty, it should raise a error. Next, we're just testing on getting all the different stats. So we add that knowledge again. You should be seeing a pattern between all these different test suites. We create a variable called stats. We call that getStats method. And everything should only equal to 1. So we should only have one topic, one total entry, and one category, since we only added one entry to that temp store. We also have test search strategies, test different search strategies. So we're adding a machine learning topic to our temp store. And now we're using different strategies. So for each strategy in this variable, we're specifying our query and the specific strategy we are using. And for each one, ensuring that there's only one result and that each score is equal to or above 70. We also have our test fuzzy threshold. So it just tests our threshold functionality. We add that knowledge or the entry to our knowledge store. We're testing it with a high threshold. So remember, this Python is missing an O. Should probably maybe get like a lower score since there's no it's looking for it's looking for this specific query, but we have Python with O all throughout our knowledge store over here. So we should not be getting any results, but if we lower it to 60, we got a result of 1. So we're testing our category based search abilities now. So we have programming as our category for this specific entry. We pass it into the query of this method, search by category. We should have one result returned. And we're ensuring that it equals to programming. So we're ensuring that the category up here equals this. We also have test list functions. So we're adding 3 different entries to two different entries to our temp store. We're calling our list all topics method and list all categories. And we make sure or ensure that we're getting 2 results back for topics and 2 for categories, and that topic 1 is in topics, so we have a topic 1, and that we also have a category 1 in categories. So that's our test file and what it checks. So hopefully you guys are able to piece everything now that we went over each file and what's happening and how they are connected. So we have done a quick test on our labrunner.py, also on our full test suite. And we can do an interactive testing. Let's go ahead and run this real quick, see what happens. So it's just saying run this Python code within our terminal. So if we have our imports, creating our store, we're adding all of this. We're adding entry to our store, and then storing our results and printing it out. So let's go ahead and press enter and run this command. Let's see what it does. So it says it found 1 results. Let's go ahead and check our knowledge.json that just got created onto our left side. So as you can see, if we're looking at this again, this specific line, this entry got added to our knowledge.json. So it has an ID of 1, content, hello world, keywords, hello and world, topic, greeting, category, general, and the date that it was added. And our search score is 0. So key learning points for today. We have fuzzy matching, understand how approximate string matching works and when to use it. Search strategies, learn different approaches, so exact, partial, token-based, best. Threshold tuning, experiment with different similarity thresholds. Data persistence, manage data storage with JSON files. And error handling, build robust application that handle edge cases.